A predicate like p of x is a statement that becomes true or false once we give a concrete value to x. Formation rules tell us how to build well-formed formulas, WFF. Start with atomic predicates such as p of x and q of y, x. Combine them with logical connectives not, and, or implies if and only if. Attach quantifiers for all x or there exists x in front of a formula. A variable is free if it is not bound by any quantifier inside the formula. It needs a value from the outside. It is bound if a quantifier explicitly controls it. Example, p of x and there exists yq of y, x. Here x is free, it appears outside any for all or there exists that mentions x, while y is bound by the there exists y. Think of a free variable as an open-ended question who, and a bound variable as a temporary name given inside a sentence, like saying there exists a person y such that. The two main quantifiers are colon. Universal for all x colon for every x. Existential, there exists x colon there is at least one x. The scope of a quantifier is the part of the formula that it governs, usually the smallest subformula to its right unless parentheses enlarge it. Example, for all x, p of x implies q of x says for every x, if p of x then q of x. If we wrote for all x, p of x implies q of x without parentheses, the scope of for all x would be only p of x, and the whole formula would mean for every x, p of x implies q of x, a very different claim. Real-world analogy colon, think of a school rule. For all x, student of x implies follow rule of x means every student follows the rule. Moving the parentheses can turn it into if everybody is a student then the rule is followed, which is nonsense. Negating quantified statements flips the quantifier and pushes the negation inside, just like De Morgan's laws for and or. Not for all x p of x is equivalent to there exists x not p of x it reads. It is not true that everyone has p means there is someone who does not have p. Not there exists x p of x is equivalent to for all x not p of x it reads. There is no x with p means every x lacks p. To apply them, move not step by step across the formula, turning for all into there exists into for all and changing each connective. Not left parenthesis a and b right parenthesis implies not a or not b and so on. Example, not for all x p of x or q of x becomes there exists x not p of x or q of x, which further becomes there exists x not p of x and not q of x. Analogy, if a manager says not all workers are late, the employee hears there exists at least one worker who is not late, a direct flip of the quantifier. When more than one quantifier appears, the order matters. For all x exists y r of xy reads for every x, there is a possibly different y such that r of xy. Exists y for all x r of xy reads, there is a single y that works for all x. These are generally not equivalent. Example with real objects, let r of xy be x likes the flavor y of ice cream. For all x exists y r of xy says everyone has some flavor they like, true for a diverse crowd. Exists y for all x r of xy says there is one flavor that everyone likes, often false. Thus switching the quantifiers can change a true statement into a false one, showing non-commutativity. Explanation. A formula is in Pernek's normal form, PNF, when all quantifiers appear at the front, followed by a quantifier-free matrix. To convert, pull quantifiers outward using equivalences while preserving logical meaning, renaming bound variables to avoid clashes. Example, convert there exists x for all y p of x or not q of y. 1. The matrix is p of x or not q of y. 2. Quantifiers already surround the whole matrix, so the formula is already in Pernek's. There exists x for all y p of x or not q of y. If we had a more tangled formula, such as for all x p of x implies there exists y q of y, we first rewrite implication. For all x not p of x or there exists y q of y. Then move there exists y outward using the rule for all xa or there exists yb is equivalent to for all x there exists ya or b, provided y not free in a. Result, for all x there exists y not p of x or q of y. This systematic process is called quantifier elimination, not removal, but extraction to the front. Natural deduction gives us inference rules that let us introduce or eliminate quantifiers safely. For all introduction, also called for all I. If you have derived P of C for an arbitrary constant C that does not appear in any open assumption, you may conclude for all x, P of x. Think of proving a rule for a generic person. Once you show it works for an unspecified person, it works for everyone. For all elimination, also called for all E. From for all x, P of x you may infer P of t for any specific term t, substituting the universal claim with a concrete example. There exists introduction, also called there exists I. From P of t, you may infer there exists x such that P of x because you have exhibited a witness. There exists elimination, also called there exists E. If you know there exists x such that P of x and assuming a fresh constant c with P of c, you can derive q without c appearing in q, then you may conclude q. This captures the idea of take an unknown witness, reason with it, and then discard the name. These rules mirror everyday reasoning. To claim all dogs bark, you first reason about a dog of your choice for all introduction. To use some student solved the problem, you pick that student as a witness, there exists introduction. Explanation. To test validity of a quantified argument, either build a formal proof or search for a counterexample and interpretation where premises are true but conclusion false. Example claim, there exists x for all y x equals y. In any domain with more than one element, no single x can equal every y, so the statement is false. A counterexample is the domain D equals the set 0, 1. No element equals both 0 and 1, so the formula fails. If the domain were a single element set of the statement would be true. Hence, the truth of quantified statements heavily depends on the domain of discourse, showing a domain where premises hold, but the conclusion does not disprove universal validity. Typical exam tasks involve 3 skills. Translation, convert English sentences into logical form. Example, every student solves some problem becomes for all x, student of x implies there exists y such that problem of y and solves of x and y. Proof, use natural deduction or direct reasoning to show an implication. Example, from for all x, P of x implies Q of x, and there exists x such that P of x, prove there exists x such that Q of x by exists elimination and for all elimination. Equivalence, show 2 formulas are logically equivalent, often by applying quantifier negation and De Morgan rules. Example, prove not exists x for all y r of xy is equivalent to for all x there exists y not r of xy step by step. Not exists x for all y r of xy is equivalent to for all x not for all y r of xy, which is equivalent to for all x there exists y not r of xy. Practicing these 3 types builds fluency with the mechanics of predicate logic. Explanation. The domain of discourse D is the set of objects that variables range over. The meaning of each predicate is given by an interpretation. Example, let D equal the set of natural numbers. Define P of x, x is even, and Q of x, x greater than 5. Then the formula for all x, P of x implies Q of x reads every even natural number is greater than 5, which is false because 0 and 2 are counterexamples. Changing the domain changes truth values. If we restrict D to 6, 8, 10, and so on, the same formula becomes true. Hence, when working with quantified statements, always keep the domain and predicate definitions in mind, just as a survey question changes meaning depending on who is being asked.